ವಿಜ್ಞಾನ ತರಗತಿಗಳು @VSR ಯೂಟ್ಯೂಬ್ ಚಾನೆಲ್ಗೆ ನಿಮಗೆ ಸ್ವಾಗತ. ವಿಡಿಯೋ ನೋಡೋಕ್ಕೂ ಮುಂಚೆ ಚಾನೆಲ್ ಅನ್ನು ಸಬ್ಸ್ಕ್ರೈಬ್ ಮಾಡಿ ಮತ್ತು ಲೈಕ್ ಮಾಡೋದನ್ನು ಮರೆಯಬೇಡಿ. ನಿಮ್ಮ ಲೈಕ್ಗಳು ಉತ್ತಮ ವಿಡಿಯೋಗಳನ್ನು ಮಾಡಲು ನಮಗೆ ಪ್ರೇರಣೆ ನೀಡುತ್ತವೆ. ಲೈಕ್ ಮಾಡ್ತೀರಾ ತಾನೇ? ಡಿಸ್ಕ್ರಿಪ್ಷನ್ನಲ್ಲಿ ಈ ವಿಡಿಯೋಗೆ ಸಂಬಂಧಪಟ್ಟ ಮಾಹಿತಿ ಇದೆ, ಡೌನ್ಲೋಡ್ ಮಾಡಿಕೊಳ್ಳಿ.
So, what in the world does a giant electromagnet have in common with a simple pair of glasses? I know, it sounds a little weird, right? But the answer is pretty amazing, and it's all about the invisible forces that are constantly shaping our world. Today, we're going to dive deep, starting with the unseen world of magnetism and ending with the science of how we see. You'll see how the very same rules can create these huge, powerful forces and also give us crystal clear vision.
All right, here's our game plan. First, we're going to get a handle on the invisible rules of magnetism. Then, we'll see how those same ideas of shaping and directing things apply to light using mirrors and lenses. And to wrap it all up, we'll see how a simple piece of shaped glass can literally fix our eyesight. Let's get into it. Okay, first up, we have to start with the basics. And that means getting to know these invisible lines of force. They're what create a magnetic field, and they basically dictate how every magnet out there behaves. So, what are these magnetic field lines, really? Well, you can't actually see them. Think of them more like a roadmap or a cheat sheet. They're an imaginary tool we use to see the invisible, to map out the direction and, just as importantly, the strength of a magnet's influence on everything around it. Super useful. Now, these lines follow a very strict set of rules, no exceptions. They always form these complete closed loops, flowing out from the North Pole and back into the South. They never cross each other. And here's the really important part. See how they're all bunched up and crowded at the poles? That's not an accident. The denser the lines, the stronger the magnetic field is in that spot.
Okay, so those are the rules for, a regular old magnet. But what if we want to make and control a magnetic field ourselves? Well, that's where this thing called a solenoid comes in. It's basically just a coil of wire, but when you run an electric current through it, boom, you've got yourself an electromagnet with a field you can control perfectly.
And here is the real magic of a solenoid. It's what happens inside that coil. The magnetic field lines snap into these perfectly parallel, evenly spaced straight lines. This creates what we call a uniform field. That means the magnetic force is the exact same strength and points in the exact same direction at every single point inside. And trust me, that's an incredibly powerful tool for everything from MRIs in hospitals to giant particle accelerators. Now, let's take that idea of invisible forces and directed fields and apply it to something we use every single day: light. We're jumping from magnetism to optics. But you'll see the core idea is exactly the same. The image you see in a mirror, it is 100% determined by the shape of that mirror. And it really all boils down to this. You've got two main types. A concave mirror curves inward. Think of the inside of a spoon. It takes light rays and brings them together, or converges them. A convex mirror does the opposite. It curves outward, like the back of a spoon, and it spreads light rays out, or diverges them. That one little difference in shape changes absolutely everything. So, for a concave mirror, the big thing to remember is that it focuses all that light down to a single point. This creates what physicists call a real image. You can actually project it onto a screen, just like a movie projector does. But with a simple concave mirror, that image is going to be inverted, or flipped completely upside down. A convex mirror, on the other hand, does the exact opposite. Because it spreads the light out, it creates a virtual image. This means the image only appears to be behind the mirror. You can't actually project it onto a wall. The perfect example is the passenger side mirror on your car. It gives you that wide, upright view of everything behind you. Okay, so we've bounced light with mirrors. Now let's talk about bending it with lenses. We're moving from reflecting light to passing it through a carefully shaped piece of glass, but you're about to see that the main principles, converging and diverging, are exactly the same. And would you look at that? See the pattern here? Just like with mirrors, it's all about the shape. A concave lens is shaped to diverge light, and a convex lens is shaped to converge it. And the results are the same too. One gives you a virtual upright image, and the other gives you a real inverted one. Here's a super simple way to remember a concave lens. It caves in. It's thinner in the middle and thicker out at the edges. And that specific shape is what makes it spread light rays apart. And yep, you guessed it, a convex lens is the exact opposite. It bulges out, it's thickest right in the middle and gets thinner toward the edges.
This is the classic shape you need to bend light rays inward and bring them all together at a single focal point.
So, why are we talking about all this? What's the point? Well, this is where it all comes together. In this last section, we're going to connect these basic rules of physics to something millions of us rely on every single day, to just see the world, our eyeglasses.
I mean, have you ever really stopped to think about it? How does that little piece of plastic or glass in front of your eye make a blurry world suddenly sharp and clear? It's not magic. It is pure, elegant physics in action. Let's break it down.
Okay, so if you're nearsighted, the technical term is myopia. Your eye is basically focusing light a little too much. The focal point ends up in front of your retina, instead of on it. So to fix it, we need to spread the light out just a tiny bit before it hits your eye. And what does that? A concave lens. It diverges the light just enough to push that focal point backward so it lands perfectly on your retina. Now, for farsightedness, or hyperopia, it's the exact opposite problem. Your eye isn't bending the light enough, so the focal point is trying to form somewhere behind your retina. So what's the fix? We need to give the light a little extra squeeze. A convex lens does just that. It converges the rays, bending them a bit more and pulling that focal point forward so it hits the retina right on the money.
And here's the final thought I want to leave you with. We just saw how these simple shapes can literally correct our vision. But think about what else that means. These exact same principles, converging and diverging light, are what let us look out into the farthest reaches of the universe with telescopes, peer into the microscopic world with microscopes, and capture our memories with cameras. It all comes back to the simple, beautiful physics of shaping and bending light. Pretty amazing, right?